Welcome back to Differential Calculus. In this video, I want to talk about optimization problems. Optimization problems is the blanket term that we use for applications that rely on absolute maximum or absolute minimums. One classic example in this type of situation is a geometry problem asking you to find the maximum volume of a box that is constructed using certain restrictions. For example, you're going to make an open box by cutting 4 corners out of a sheet of paper and then folding the sides up to turn it into a container. Another classic example of optimization problems involves looking at situations where rates are different in two separate types of situations. That's what I want to look at here. So if I get my head out of the way, I can put up this giant wall of text. An island is 500 feet north of its closest point along a straight shoreline. A beachgoer is 1,500 feet west of that point and wants to go out and explore the island. She can jog on the sand at 10 feet per second and can swim at 4 feet per second. How far should she jog down the beach before getting in the water to minimize her travel time? All right, that is a wall of text. Let's try to turn that into a picture. So we have a shoreline. It is a relatively straight shoreline, and there is an island somewhere in the water. We have a person who is on the beach who wants to get to that island. All right, let's see. We know that the distance like this is 500 feet, and the distance here is 1,500 feet. This person is going to go along the shoreline for some amount of distance, we'll call it X, and then get into the water to travel the rest of the way in a straight line like that. So the first thing that I want to do is figure out the distance here. If I call this distance x, what is the distance that, if I call this distance that the beachgoer is going to jog x, what is the distance out here that the beachgoer is going to swim? Well, if I get rid of all of the detail in this picture, I realize that the situation I am looking at has a right triangle. This leg of the triangle is 500 feet. This distance over here is x, and since the total distance across the bottom is 1,500, the bit of that is on the triangle is 1,500 minus x. And using the Pythagorean theorem, we get that the distance here is going to be the square root of 500 squared plus 1,500 minus x, all squared. All right, we can go through and do a little bit of algebra to clean that up. 500 squared is 250,000. 1,500 squared is, dropping my calculator, 2,250,000. And then we'll have minus 2 times 1,500, which is 3,000 x, and we'll have a plus x squared. Combine some like terms. we're looking at the square root of 2,500,000 minus 3,000x plus x squared. Right. So that's the distance that our beachgoer is going to swim, which is an important part of the process, but certainly not the whole thing. Scrolling back up, we are looking to minimize her travel time. So we need to go from distance to time. Using the classic rate equation, distance is rate times time, then time itself is distance divided by rate. And I know that this person is going to be running. I'm sorry, not running, jogging. The distance that this person is going to jog is x, and the rate at which she jogs, if I scroll back up to the text, is 10 feet per second. Our beachgoer is also going to swim. The distance she is going to swim is this wonderfully simple expression, 2,500,000 minus 3,000x plus x squared, and the rate at which she swims is 4 feet per second. So if we add these together, we have the total time. I'm going to put a box around that so I don't lose it. This is our object function, or sometimes our objective, in the language that we often use for this type of problem. Our goal is to find the minimum value of t. And to do that, we notice that this expression defines t as a function of x, which is completely backwards of how we ever think about that, but it works for this problem, so we're happy. All right, t is a function of x. I can even go in there and explicitly write that t is a function of x. Our goal is to find the absolute minimum of t. And I guess we have to think a little bit about whether that's going to even be a thing. It is in this case, but it's worth thinking about. Well, going back to our picture, if I scroll up a little bit here to the picture I have, I made an implicit assumption here that I think is fair. Our beachgoer is going to run along the sand. They might choose to not jog along the sand at all and immediately get in the water and make the direct swim across. If the person swam faster than they jogged, or even swam and jogged at the same rate, that would be the best choice. Our beachgoer could jog down the beach all the way to the closest approach and then swim out. That could be reasonable. I can imagine a world in which that is the best choice. One thing that I know for certain, our beachgoer is not going to start by jogging this way and then swimming. That is definitely going to add time that we didn't need. Likewise, our beachgoer is not going to jog way past and then swim back. That is also going to add time that we didn't need. Because we're looking for the minimum time, the beachgoer is going to either jump right into the water, come all the way down and jump in the water, or most likely something in between. So we are looking for the absolute minimum of t for x, that's not the yellow pen, x in the interval from 0 to 1500. That is looking for the minimum of a function on a closed interval. It looks like this is likely going to be a continuous function on that interval. I feel fairly confident that we're not going to find a time somewhere in there where it's infinite, although I haven't taken the time to actually analyze that square root. I would rather avoid that if I can, because that's kind of nasty. But that gives us something to work with. That gives us, by the extreme value theorem, the absolute minimum should exist. It's just a question of finding it. And to find it, we are going to take the derivative. We're going to identify some critical values. All right, the derivative of 1/10 x is just 1/10. The derivative of the square root of this whole mess is going to be 1/2 times the square root of the whole mess. Then, using the chain rule, multiply in the numerator by the derivative of all of that stuff, which will be negative 3,000 plus 2x. All right. This could be undefined at a point if I have to worry about what's going on inside that square root. So let's go off to the side here for a moment and just check that. If 2,500,000 minus 3,000x plus x squared is equal to 0, then our derivative is undefined, and undefined points are critical values. All right, I don't want to try to do this by factoring, so I'm going to jump right into the quadratic formula. X equals 3,000 plus or minus the square root of 3,000 squared minus 4 times 2.5 million times 1 all over 2 times 1. All right, my calculator tells me that 3,000 squared is 9 million. Subtract, 4 times 2,500,000 is 10 million. So we have 3,000 plus or minus the square root of negative 1 million. And negative 1 million underneath the square root gives us imaginary roots. All right. We are only looking for real values. Again, this is a very apparent case. We're dealing with somebody running down the beach. you can't run an imaginary distance down a beach. So the fact that this comes out as imaginary values, for our purposes, tells us that the derivative is continuous everywhere on our interval. All right, it was worth checking at some point, recognizing that we don't have anything to worry about. The stuff underneath that square root is just going to stay positive for us. And now that we know that, we can continue onward. I'm going to get this out of my way, not because it wasn't important to write down, but because I only have so much space. And it helps if I use the right tool. I want the eraser, not the selector. I don't want to copy this, I want to get it out of my way. All right. So again, I wouldn't erase this from my notes. I would include that as something that's useful, but I want to be able to work with this formula some more. So let's get everything else out of the way. I can set this equal to 0. Subtract 1/10 and then multiply by 8 to get rid of the fraction in front and get rid of the extra term. And I have that negative 3,000 plus 2x over the square root of 2,500,000 minus 3,000x plus x squared is equal to negative 8/10. From here, the cross product test looks appealing to me. And then get rid of the square root by squaring both sides of the equation. All right, negative 30,000 squared is positive 2, 3, 4, 5, 6, 7, 8, 900 million. And then we have 2 times negative 30,000 times 20, which is going to come out as minus 12, and that should have 1, 2, 3, 4, 5 zeros on it. So 1,200,000 times x, and then we'll have 20x squared, which is 400 times x squared. This is equal to negative 8. Well, negative 8 squared is positive 64 times the square root of that stuff squared is just the stuff that was inside, 2,500,000 minus 3,000x plus x squared. Distribute that. So we have 160 million minus 192,000 times x plus 64 times x squared. Move everything to the left-hand side of the equation by subtracting the right-hand side of the equation. So 900 million minus 160 million comes out at 740 million. We have minus 1,200,000 plus 192,000, which is going to be minus 1,008,000 times x. And then we have 400x minus 64x, which is 360. I'm sorry. There we go. Come on. 336x squared That's now equal to 0. That should be plus. There we go. At this point, I'm tempted to divide both sides of the equation by at least 4. But I think I'm just going to leave it at that, and I'll deal with it after I use the quadratic formula. So x itself is going to be the opposite of 1,008,000 plus or minus the square root of 1,008,000 squared minus 4 times 336 times 740 million all divided by 2 times 336. All right. Now let's hope that I got everything into my calculator correctly. So 1,008,000 squared minus 4 times 336 times 740 million. My calculator tells me is too big. All right, my calculator switched into scientific notation in order to write that out. So I'm not going to try to write that step in. I'm just going to take the square root of the number. The only thing that mattered was it came out positive. And then when I take the square root, I get 146,642 and change, but I'll round it to the nearest whole. That seems like it's more than good enough. 2 times 336 is 672. And now, last step. I get something on the order of 1,718. And I get something on the order of 1,282. Those are our two possible critical values. If I scroll all the way back up, where was it? There it is. We are only interested on this interval between 0 and 1,500. This is not in the interval. This one is. All right. I think that this video has gotten long enough. I claim, without having gone through it, that the answer here is going to be to jog for 1,282 feet and then swim from there to the island. What I'd like you to do is think about what we've talked about with the extreme value theorem and finding absolute extrema in the past, and set up the rest of this. Think about what we have, think about what there is left to test in order to verify that jogging for 1,282 feet is the correct answer. What other answers are still possible that we haven't ruled out yet? And then take the time to rule those out and show that they give longer times than this one. All right, see what you can do with that one, and I'll see you in the next video.